This is lab 4 for physics 2. In this experiment, the goal was to measure the magnetic field of a magnet at different distances and intensities both on and off the axis. So we used the magnometer app Firefox. We measured the magnetic fields due to a permanent bar magnet. This allows us to use our understanding of the Biot-Savart law as well as modeling a magnetic field with GlowScript. So some physics principles we use. The Biot-Savart law relates magnetic field at a point to a tiny current element, the magnetic field of a dipole, and that's caused by the closed circulation of an electric current system. And the distance dependence formula, the magnitude of the magnetic field due to a bar magnet falls off with distance. Some equations we use. The first equation given is the equation we use to calculate magnetic field. In this equation, mu naught is a constant and r is our observation vector. Mu itself is the magnetic dipole moment we must calculate. The second equation represents the magnitude of the magnetic field. N is supposed to be -3, so we can also calculate percent error of this experiment through our own experimentally calculated n. However, the real value of this equation comes from the way we can rearrange it, which is taken in the third equation where we take the natural log. This is the format of the line equation, which makes it easier to analyze and extract the value of k from it. We use this line equation format to use in our experiment. So here's the procedure. So we download the app to the phone and then make sure the app compensates for the Earth's magnetic field, ensuring the app is reading the field from the bar magnet and not skewed by the Earth's field. So you can see for the procedure, we slide the phone along the perpendicular line, and then we repeat that to find the place where the magnometer is on the phone. And then we make all our measurements requested on axis and add the data points to Excel spreadsheets as said in the instructions. So this slide shows all the data gathered in this experiment. The graph shows the equation with the same structure as the equation slide. Using that equation, we can solve for the value of k by putting the y-intercept to the power of e. This eliminates the natural log. So the value of k from the data is equal to e to the negative 15.756. This value is important in finding the magnet's overall dipole moment, which we discussed on a later slide. The graph was made from the distance, with certain intensities on the axis. The calculations for the off-axis field are at the bottom of the slide. So here's the GlowScript code. To begin, this is the starter code, and we added a constant from the constant section, which was the value of e that we got. Next, I calculated the value of the magnetic constant. Using the line equation from the previous slide, I inputted how I got my value of k into the code. I then calculated mu magnitude by dividing k by mu naught and 2. Then I printed this value to the computational model. The next thing I did was edit the function that generated the magnetic field. I calculated the magnitude of r and r hat. Then I used the equation for finding b that we showed in the equation slide and discussed earlier. The B scale and distance are both used to help make the model easier to understand and scale. The distance can be changed to show the field at different distances. I edited the observation location vectors to create 6 vectors that were at a max and minimum distance of each component of the vector, x, y, and z. Then I drew 2 arrows to represent the magnetic field on the axis. The radius for these arrows was from the observation axis at that point to the magnet's position. The 2 observation locations were at 0.2 and negative 0.2 meters away to show the field if the magnometer was 20 centimeters away from the magnet. Next, I drew the arrows to represent the magnetic field perpendicular to the axis. This represents the field I observed measuring off-axis. The process for drawing these is similar to the arrows drawn on axis, the only difference being the observation location for the calculation of the radius. First, I determined the observation location perpendicular to the axis, then calculated the magnetic field at the location due to the dipole moment. Then I drew the arrow to place in the model. The last segment of code on the bottom right is used to draw the magnetic field 45 degrees off-axis. I used my average perpendicular distance from the Excel spreadsheet and found the actual distance r between the magnometer and the magnet using triangle rules. Then created the vector of the observation location 45 degrees away. Then, just like the other arrows created, I found the radius between the 45-degree location and the magnet. I then calculated the magnetic field at that point and drew an arrow. This completes the GlowScript. And this is the model printed by my code, with the orange arrows representing the magnetic field calculated on axis and the cyan arrows representing the magnetic field calculated perpendicularly off axis. The orange arrows point in the direction of the magnetic dipole moment, while the blue arrows point in the opposite direction. Then, furthermore, the perpendicular vectors are half the magnitude of the on-axis vectors. This means the magnetic field of the bar magnet is only half as intense at points perpendicular distance away as compared to the field on-axis, and the magnitude of the magnetic field decreases as the distance increases. So these are the values outputted by the code. The overall magnetic dipole moment was calculated to be around 0.718 joules per Tesla. The magnetic field vector of the on and off axis calculation are shown below. Finally, magnetic field magnitude is 45 degrees out, 6.07 times 10 to the 6th. Here are discussion questions. If we hadn't oriented the compass to compensate for magnetic north, all the magnetometer readings would have been incorrect, and then if we were to stick two identical magnets together, there would be no impact.